Hello everyone. Today I am going to discuss compound pendulum or physical pendulum. Let us understand what is compound or physical pendulum. Compound pendulum is a rigid body of arbitrary shape which is capable of oscillating in a vertical plane about a horizontal axis such that the axis do not pass through its CG. So I am writing it is a rigid body of arbitrary shape which is capable of oscillating in a vertical plane about a horizontal axis such that the axis do not pass through the CG. Okay, so I'm writing CG do not pass through the CG. So let me draw a compound pendulum here. Okay, this is a compound pendulum of arbitrary shape. Clear? Now it is in a vertical plane. Okay, so if I draw axis XY and Z axis is perpendicular to this board. Okay, so we can see compound pendulum is in XY plane. Okay, and the axis is horizontal, so this is an axis, so this is the point of suspension. Okay, this is S, so this is point of suspension, or it is also called a pivot. Clear? Now this pendulum is of arbitrary shape and we find there are distributed point masses. This pendulum is made from large number of distributed point masses. Okay, so let me erase this. Okay, now initially it is at rest. Clear? This is at rest. So if the pendulum is at rest, then the center of gravity, and let us denote the center of gravity by the symbol G, lies directly below the point of suspension, and let this distance, that is SG, be L. Okay, so once again I repeat, if the pendulum is at rest, then the center of gravity lies directly below the point of suspension. Okay, this is the point of suspension, so I am writing point of suspension. Okay, and this is the center of gravity. Now suppose if we displaced the pendulum, okay, by small angle, let us displace the pendulum by small angle. So it will be at the new position. Okay, so if we displaced it by small angle theta, okay, then this is the new position of the center of gravity. Clear? Now the distance s g dash is again same. Okay, this is L. Now we are displacing this pendulum in anti-clockwise direction, okay, by angle theta. Now once we remove the external force, then due to restoring torque, the pendulum tries to come back to its original position. So we need to find the restoring torque. Clear? We are displacing the pendulum by angle theta in anti-clockwise direction, and due to restoring torque, okay, due to restoring torque, the pendulum tries to come back to its original position. The restoring torque is due to the gravity. Okay, the restoring torque is due to mg. Okay, now we need to find the restoring torque. Clear? We need to find the restoring torque. So in order to find the restoring torque, okay, so let me erase this figure. Okay, or let me draw this figure. Okay, here. This is the horizontal axis. Okay, this is a vertical line. So we have G. This is point S. Okay, so I'm drawing the displaced figure. Okay, this is the displaced position. Okay, now the pendulum is displaced by small angle theta. Okay, this is G dash, center of gravity when the pendulum is displaced, and this is angle theta. So the distance SG is L and distance SG dash is L. Okay, now as I said earlier, the restoring torques comes into play, and the restoring torque is due to gravity. Okay, or is due to this force, that is mg. Now what happens is that there exists a torque and we need to find the torque. Okay, now at point S, and this is called the center of or point of suspension. Okay, so let me write over here, this is point of suspension. So at point of suspension, okay, there exists a reaction force. So this is a reaction force. Okay, and we have force mg acting in downward direction, vertically downward direction. Okay, so let me erase this. Now we know torque equals force times perpendicular distance. Okay, in magnitude. So we need to find the perpendicular distance. So let me draw over here. Okay, this is point S. So this is G dash. Okay, the displaced position of CG. So we have force mg acting vertically downward direction. Okay, now we have two force. One is reaction force acting in vertically upward direction, and next, okay, mg acting vertically downward direction. So as I said earlier, the restoring torque is due to mg. Okay, so force is mg. Now we need to find the perpendicular distance. So in order to find the perpendicular distance, so let me produce this force in downward direction. Okay, and let us drop perpendicular from G dash on this dotted line. So this is N, and we can see from figure this angle is theta. Okay, so let me draw perpendicular from G dash on this line. Okay, so this is N, and let us denote this angle. Okay, and this is 90 degrees, so I'm denoting it by the symbol. Okay, so 90 degrees. So we need to find perpendicular distance. Okay, and G dash. So, and for restoring torque, we need to put negative sign. Why? Because as I said, we have displaced the pendulum from initial position by angle theta. Okay, and if we see the direction of rotation, then it is anti-clock or anti-clockwise direction. Now due to restoring torque, okay, the pendulum tries to come back to its original position, so that the torque, that is restoring torque, produces the rotation in clockwise direction. So for that reason we put negative sign. Okay, so let me erase this. So I'm writing over here, so let me use the different ink. Okay, now restoring torque tau equals force is mg. So let me put negative sign also. Okay, for restoring torque, mg times perpendicular distance is n g dash. Okay, so here m is the mass of this pendulum, so do not get confused. Okay, so m, so let me write over here, m is mass of pendulum. Okay, m is mass of pendulum, clear? And we know g is 9.8 meter per second square. Okay, now we can write tau equals minus mg. Now let us find ng dash from this figure. So we can see from this figure sine theta. Okay, this is ng dash by perpendicular by hypotenuse. Yes, so ng dash by s g dash, and s g dash is L. So we can write ng dash, okay, equals L, s g dash is L times sine theta. So this is restoring torque. Clear? This is restoring torque. Sorry. So this is equation 1. Now we have displaced the pendulum by small angle theta. Okay, so we know the expansion of sine. Okay, expansion of sine theta. Sine theta is expanded, okay, in this form. Sine theta equals 1 minus theta cube by 3 factorial plus theta phi by 5 factorial minus dot 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 so on. And in case of cos, we have, sorry, this is theta, sorry. So the first term is theta, okay. In sine, theta minus theta cube by 3 factorial plus theta phi by 5 factorial, okay. And again we have minus, clear, and so on. So in case of cos, the first term is 1, okay. Now if theta is small, then higher power of theta, that is theta cube, theta 5, can be neglected, okay. So let me write over here, then theta cube comma theta 5 can be neglected, okay. They are very small. So we can write, therefore sine theta is nearly equal to theta or approximately equal to theta. And as I said, for cos theta, the first value is 1, so that if theta is very small, for cos we get approximately cos theta equals 1, okay. So let me write over here, okay. If theta is small, then sine theta is approximately or nearly equals theta, okay. Therefore from 1 we get torque tau equals minus mgl theta, okay. So this is the restoring torque. So let us call this equation 2, okay. So let me erase this for okay. Now let us compare linear motion with rotational motion. So in this case we have rotational motion, okay. So let me explain in short, okay. Linear and rotational, okay. For linear motion, okay, we have force F, and for rotational motion, okay, we use torque, okay. Torque, force is replaced by torque, though force and torque are not the same, okay. Torque is, or torque plays the same role as that of force in rotational motion. For linear motion, we take linear acceleration, and for rotational we take angular acceleration. And for linear we have mass, okay. For rotational motion we take moment of inertia. Moment of inertia plays the same role as that of mass in linear motion, okay. Now for linear motion we take linear displacement x, okay, or linear distance x. And for rotational motion we take angular displacement theta, okay. Now for linear motion we use F equals m times a, and for rotational motion we use torque tau equals I times alpha, okay. So we use this equation, tau equals I times alpha. Now we can write we know tau equals I alpha. This is relation number 3, where I, so I'm writing, where I, this is moment of inertia, and alpha is d square theta by dt square, and this is angular acceleration. Okay, now we can equate 2 and 3, so we can write from 2 and 3 we get, okay, I alpha. So let me change the ink also. Okay, we can write I alpha equals minus mgl theta. Okay, so I and alpha is d square theta by dt square equals minus mgl theta. So on rearranging, we can write d square theta by dt square plus mgl by I. So let me put this in a bracket. Okay, theta equals 0, and this is relation number 4. Okay, we are getting a differential equation, that is second order differential equation in term of theta. Now let us do some rough work. Okay, now let us find this term. What is this term dimensionally, or what is the unit of this ratio? Okay, mgl by I. Okay, m is mass, it is kg. Okay, g is acceleration due to gravity, meter per second square. L is the length, we can see from figure, so it is in meter. And I is moment of inertia. Moment of inertia is mass time square of the distance. So we can write I as, okay, or the unit of I is kg meter square. So kg cancels out. Okay, and meter square. Okay, this meter square and meter square cancels out. So the unit, okay, the unit or dimension, we can say the unit of mgl by I is 1 by second square. Okay, now we know angular frequency omega equals twice pi f equals twice pi by t. Now let's take the square of this. Okay, so omega square equals 4 pi square by t square, and 4 pi square, okay, this term 4 pi square do not have unit. Clear? So that the unit of omega square is, so let me write over here. Clear? The unit of omega square, okay, is 1 by second square. So this ratio has the same unit as that of omega square. Okay, so that we can replace this ratio by omega square. So this is mathematically, okay. So you can also directly compare this equation with the standard differential equation, where you get omega square. Okay, but I am doing or justifying that this ratio is omega square mathematically, okay, by considering the unit. So let me erase this. So we can write, let omega square equals mgl by I. Therefore, from 4, okay, we get d square theta by dt square plus omega square theta equals 0. So this is the differential equation for compound pendulum. Okay, so this is the second order differential equation for compound pendulum. Now we are interested to find the time period of compound pendulum. Clear? So we need to find the time period of compound pendulum. So in order to find the time period of compound pendulum, we use this relation, okay? Omega square equals mgl divided by I, that is moment of inertia. Clear? So let me erase this, okay? Now let us find the time period. We have omega square equals mgl by I, okay? So we take this. So let me erase this, okay? Now we know omega equals twice pi by t, okay? So we can write twice pi by t, and we have a square, okay, equals mgl by I. So 4 pi square by t square equals mgl by I. So we can write t square equals, on cross multiplying, okay, we have, or we get 4 pi square, clear, I by mgl. So on simplification we can write t equals twice pi under root I by mgl. So this is the time period of compound or physical pendulum. Okay, we use this relation in various numerical problem related to the compound or physical pendulum.